Welcome to our third lecture in this series of force systems. In this lecture, we will discuss coplanar systems. There are two types of coplanar force systems. If all lines of action of the forces in a system intersect at one point, the force system is called concurrent. Otherwise, the force system is called non-concurrent. And we will use these two systems as we venture through more structural engineering. We're going to start by looking at the concurrent coplanar force systems. Since lines of action of all forces of concurrent systems intersect at one point, the rotational equilibrium condition is automatically satisfied at the point. That is, the sum of moments at this point equals zero. Therefore, only two equilibrium conditions should be satisfied, including the sums of all horizontal and vertical components of forces equaling zero. When writing equilibrium equations, it is essential to adhere to a sign convention. In this series of lectures, we are going to assume that upward and rightward are the positive directions for forces and counterclockwise rotation is positive for moments. The components of a force in the horizontal x and vertical y directions can be found using the inclination angle to the x-axis. Let's write the translational equilibrium equations for the three concurrent forces, where F1 is inclined at the angle phi to the negative direction of the x-axis, F2 at the angle theta to the positive direction of the x-axis, and F3 acts vertically downwards. The components of the forces F1 and F2 in the direction of the x-axis can be found as the magnitudes of these forces times the cosines of the corresponding angles. The components of the forces F1 and F2 in the direction of the y-axis can be found as the magnitudes of these forces times the sines of the corresponding angles. The resulting system of forces consists only of the forces acting in the x and y directions. The sum of forces in the x direction comprises only the horizontal components of forces F1 and F2. Assuming that rightward is positive gives that the component of forces F1 is negative. This equilibrium equation leads to a relationship between forces F1 and F2. The sum of forces in the y direction comprises the vertical components of the forces F1 and F2, as well as force F3. Assuming that the upward direction is positive gives that the force F3 is negative in this equilibrium equation. The second equilibrium equation defines a relationship between all three forces. The equilibrium of the concurrent system of forces can also be analysed graphically, using the vector addition of forces. It results in a force polygon, which becomes a force triangle in the case considered here. To build the force triangle, the forces are moved in parallel to their lines of actions using the head-to-tails method. If the forces combine into a closed system, that is, when the head of the last vector coincides with the tail of the first vector, the system of forces is in equilibrium. Now let us look at examples of concurrent systems of forces in real structures. Here you can see the canopy at Lord's Cricket Ground. This is supported by masts and cables. Let's consider the junction connecting a beam with several cables. The beam and cables apply forces on this junction, which combine into a concurrent system. The cables will be in tension while the beam is in compression. Since the junction is not moving, the forces are in equilibrium. We can find more concurrent systems of forces at every other junction in this structure. This is the Olympic Stadium in Munich, built in 1972. Let's look at a few pictures of the canopy above the stadium. In the junction shown in this picture, the strut is supported by two cables. The strut applies a compression force on the junction, while the cables apply a tension force. Here you can see another two examples of concurrent systems of forces at the tops of masts. Cable cars are also supported by concurrent systems of forces. Let's see how. This is the dynamic earth in Edinburgh. This fabric canopy is supported through several concurrent systems of forces. Here you can see one of them. Now we're going to look at a crawler crane in more detail. To understand how this crane lifts loads, we need to find how forces go through its structure. In other words, we need to find the load path. We start by drawing lines of actions of forces. In the structure of this crane, forces can be transferred by cables and masts. Now we add arrows in the direction of forces. Lifting an object will require the application of an upward force equal to the weight of the object. Since cables transfer tension forces and masts in the crane transfer compression forces, the direction of the forces will be shown as in the picture. Now we'll consider one concurrent system of forces in this crane. To do that, we will create an imaginary cut by drawing a circle around one junction and removing all other forces. Now we extract the system of forces from the picture to create a free body diagram of the junction. The concurrent system of forces acting on this junction consists of three forces. The directions of F1 and F3 correspond to tension in the cables, and the direction of F2 corresponds to compression in the mast. F1 is vertical, F3 is inclined at 30 degrees, and F2 at 60 degrees to the horizontal direction. We continue resolving the forces F2 and F3 into horizontal and vertical components. Let us write the equilibrium equations. The sum of forces in the horizontal direction includes the components of horizontal forces F2 and F3. In this equation, the positive direction is rightwards. The sum of forces in the vertical direction includes the vertical components of forces F2 and F3 as well as the force F1. In this equation, the positive direction is upwards. Taking into account that F1 equals 10,000 kilonewtons, the two equilibrium equations give the following values of forces for F2 and F3. Forces F2 and F3 can also be found graphically using vector addition and building a force triangle. The force triangle is built using the heads to tail rule. Since the magnitude of F1 is known, we select the length that represents 10,000 kilonewtons. Then we draw F1 and the lines parallel to F2 and F3 from the heads and tails of F1. The point intersection of these defines the lengths that represent the values of the magnitudes of forces F2 and F3 in the scale selected. Alternatively, the magnitudes of the forces F2 and F3 can be found using trigonometrical formulas. The other type of force system is non-concurrent. The equilibrium of a non-concurrent system of forces requires satisfying three conditions. The sum of forces in the horizontal direction should equal 0, the sum of forces in the vertical direction should equal 0, and the sum of moments should equal 0. The sign convention will stay the same, namely upwards and rightwards are positive for forces and counterclockwise is positive for moments. A typical example of a non-concurrent system of forces is a simply supported beam. This beam is supported at its ends, has a length of L, and is loaded in the middle by a concentrated load of 50 kilonewtons. Let us consider the equilibrium of this beam. Due to the absence of external forces in the horizontal direction, this beam does not have a horizontal reaction force. Therefore, the sum of forces in the horizontal direction is 0. The sum of forces in the vertical direction includes the reactions Ra and Rb, and the concentrated load of 50 kilonewtons. Note that the reactions are positive and the load is negative because the positive direction is upwards. This equation defines the relationship between the reactions. Next, we select a point which is used to consider the rotating actions of forces. It is convenient to select one of the supports. Let's write an equilibrium equation of the sum of moments around the support A. Since point A is on the line of action of Ra, this reaction force will only push the point. To stress this, there is no perpendicular distance between the force and the point of action to create a rotation. As a result, only the concentrated load and Rb will rotate around the point. Remember that moment is force times distance. Assuming that the positive direction of rotation is counterclockwise, the sum of moments will include the concentrated load times the lever arm, L over 2, and Rb times the distance, L. The first term in this equation is negative because the concentrated load rotates clockwise. The second term is positive because Rb rotates counterclockwise. Resolving this equation gives that Rb equals 25 kilonewtons, and now we can find Ra using the first equilibrium equation as Ra equals 25 kilonewtons. As a result, both reaction forces are identical, which is characteristic of a symmetric beam with symmetric loading. Another example of non-concurrent system of forces is a ladder resting against a smooth wall. We will assume that this ladder is at rest and is restricted at the bottom end from movement. As a result, there are two reaction forces, Rb and Rc, in the vertical and horizontal directions at the bottom end. We also assume that the reaction force Ra on the smooth wall is horizontal. The ladder has a weight of 1,000 newtons. To find the reaction forces, we apply the weight of the ladder at the centre of gravity in its middle. The distance from the bottom end of this ladder to the wall is 2 meters, and from the top end of the ladder to the floor is 5 meters, as shown in the figure. We'll start with rotational equilibrium. We'll select the point O at the bottom end of the ladder and write the sum of moments around this point. The reaction forces RB and RC push point O, while only the reaction force Ra and the concentrated load of 1000 Newton rotate around it. Therefore, the rotational equilibrium equation has only contributions from Ra and the concentrated load. The contribution of Ra is negative because Ra rotates clockwise around O, and solving this equation gives that Ra equals 200 newtons. Now we can find the reaction force Ra from the sum of forces in the horizontal direction. Now we can find the reaction force Rc from the sum of forces in the horizontal direction. This equation has contributions from Ra and Rc, where the contribution of Rc is negative. Solving this equation results in Rc being 200 newtons. Reaction force Rb can now be found from the sum of forces in the vertical direction. This equation consists of a positive contribution of Rb and a negative contribution of 1000 Newton load. Solving this equation results in Rb being 1000 newtons. And that's it. We have looked at forces, concurrent systems and non-concurrent systems. And I think we're ready now to tackle quite a lot of structural engineering problems. Join me to solve examples, and in the meanwhile, bye for now.